Multiplicative inverses, no matter what size the matrix has, would still end up in an identity matrix. Learn how it is proven here in numerical solutions to CE problems. The property for multiplicative inverses suggests that the product of a matrix and its inverse will always be an identity matrix. In mathematical statement, we say matrix A times its inverse is equal to I. This property will be proven using a certain matrix A with the following elements as shown. We start with solving the inverse, and that is through its adjoint divided by its determinant, where the adjoint can be broken down as transpose of the cofactor of the matrix divided by its determinant. So let's start looking for the cofactor of matrix A. With matrix A being 4 by 4, the cofactor Aij would also be the same size. The 16 elements in the cofactor matrix are solved using determinants, so we take the minors first. For element A11, row 1 and column 1 will be covered, and the remaining elements are the minors, comprising A11. So we place them in the first determinant. If we look for A12, we cover the second column and get the remaining elements as 2, -3, and 2 in the left, and the others in the right. These will be placed in the second determinant spot. When we cover the third column, we can look for the cofactor of element 1, 3. The minors for this determinant are 2, 3, -3, 0, 2, and -2, along with the elements on the other side, -1, -2, and 4. By eliminating the fourth column, we get the minors as boxed for the determinant of A14. Completing the first row cofactors, we do the same for the second row. So cover the second row and start with the first column. The remaining elements are -2, 0, and 2, then 0, 1, and -2, with -2, 3, and 4. Now covering the second column leaves the minors 1, 0, 2, -3, 1, -2, 2, 3, and 4. They fill up the determinants for element A22. With the third column covered, element 23 has the minors 1, -2, 2, -3, 0, -2, then 2, -2, and 4. Finish the second row determinants by covering the fourth column, and have the remaining elements as minors for determinant row 2, column 4. So move to the third row. The minors for the first element A31 are -2, 0, 2, 3, 5, -1, -2, 3, and 4. The third row and column 2 covered would leave elements 1, 0, 2, 2, 5, -1, 2, 3, and 4. All elements are placed in element 3, 2. Third row, third column element A33 has the elements 1, -2, 2, then 2, 3, and negative 1, and 2, negative 2, and 4. Let's complete the third row by filling out element A34. Those elements remaining after the cover are placed in the determinant. We are now at the fourth row. Covering the first column gives negative 2, 0, 2, 3, 5, negative 1, 0, 1, and negative 2 be the minors for the determinant. Move to the second column and get the uncovered elements as minors for element A for 2. With row 4 and column 3 covered, we get 1, negative 2, 2, and then 2, 3, negative 1, negative 3, 0, and negative 2. And finally, we have the last element A for 4 minors by covering row 4 and column 4. After identifying the minors of each element, we solve for the determinant. Let's have some sample computations for this step. Say we take the determinant of element 1, 1, and that is done using Sarah's rule. Sarah's rule requires the two first columns mirrored to the end, then we compute for the positives, starting with the first with 3 times 1 times 4, which is 12. The next diagonal is solved through 5 times negative 2 with negative 2, which gives 20. Then the last main diagonal has elements negative 1, 0, and 3, which is 0. Now let's solve the negatives by taking the product of the anti-diagonal elements. Those are first, negative 2 times 1 times negative 1, which gives 2. Next is 3 times negative 2 times 3, which is negative 18. Then 4 by 0 by 5, giving 0. So we compute element A11, and don't forget the sign outside the bars. There is positive of 12 plus 20 plus 0 minus the negatives, which include 2 minus 18 plus 0. This can be simplified as 48. So element A11 is positive 48. Let's solve another sample in element A12. Note that the determinant has a negative sign before the bars, and it should be included. Use Sarah's rule once more to keep the computation clean. The main diagonals have 2 by 1 by 4, which is 8. Then the second diagonal has 5 by negative 2 and negative 2, which gives negative 20. And last main diagonal is the product of negative 1 times negative 3 times 3, which is 9. Now solve for the negatives, starting with the first anti-diagonal with elements 2 times 1 times negative 1, which makes negative 2. The second diagonal has 3 by negative 2 and another 2, and that is negative 12. The last diagonal is 4 times negative 3 times 5, giving negative 60. Subtract the negatives from the positives to have element A12, and that would be negative of the quantity, which includes 8 minus 20 plus 9 minus the negatives, negative 2 minus 12, and minus 60, which is simplified as 71. Including the sign before, we get A12 as negative 71. Let's have another practice in solving determinants of small matrices, so focus on the solution of element A13. Again, mirror out the first two columns, then mark diagonals. The first one has elements 2, 0, and 4, which becomes 0 when multiplied. The next diagonal has 3 by negative 2 with another 2, which gives negative 12. Then the last diagonal has negative 1 times negative 3 times negative 2, resulting to negative 6. Take the negatives, where the first diagonal has 2 times 0 times negative 1, which is 0. The next has negative 2 with negative 2, then 2, making 8. Then last is with 4 times negative 3 times 3, resulting to negative 36. Element A13 is then the positive of 0, minus 12, minus 6, minus the results in anti-diagonals, which are 0, positive 8, and negative 36. These are simplified as 10, so element A13 is positive 10. Let's take another solution for determinants to complete the first row. The diagonals start with 2, 0, and 3, and that is 0. The second diagonal has 3, 1, and 2, which makes 6. And lastly, 5, negative 3, and negative 2, giving the product of 30. The negatives are then solved first as 2 times 0 times 5, which is 0. The second diagonal has negative 2 times 1 times 2, giving negative 4. And last, 3 times negative 3 times 3, or that is negative 27. Element A14 is then the negative of 0 plus 6 plus 30, minus the negatives of 0, minus 4, minus 27. The figures are simplified as 67, and by placing the sign before the bars, we have A14 as negative 67. By doing the same solution for the rest of the 3 by 3 matrix, the cofactor of matrix A has the following elements as shown. Now we are to transform this matrix into adjoint, and that is merely taking the transpose of the cofactor. So the adjugate of A shows the following elements. Having identified the adjoint of matrix A, we have a quarter of the solution finished. So we move to identifying the determinant of the matrix. From the original matrix A, which is 4 by 4 in size, we need to have to reduce two smaller determinants so we can use Sarus rule. We can reduce this by focusing on the first row, and then add the alternating positive and negative signs of the elements. The elements of the first row are used as scalars to the 3 by 3 determinants, where the signs are already included. Then work on cofactor method, starting with the first column, leaving the following elements, and place them in the first determinant with 1 as multiplier. The determinant for the second term can be identified by covering the second column. The remaining elements are then placed in the second term's determinant. When we cover the third column, we get the elements for the third term. Nevertheless, the scalar for this term is 0, which cancels out all the third term. Lastly, cover the fourth column for the last term. The scalar is minus 2, and the elements are 2, 3, 5, then negative 3, 0, 1, and 2, negative 2, and 3. When each determinant is simplified, the first comes out as 48, the second results to 71, the third is 10, and the last determinant is 67. Now, the determinant of matrix A is 1 times 48 plus 2 times 71 plus 0 times 10 minus 2 times 67, which is simplified as 56. Now that all parts of the equation for inversion are figured out, we can work on the inverse of matrix A as 1 over the determinant of 56 times the adjoint of the matrix. The determinant becomes a scalar that we use to divide all elements in the matrix. So the outcome is A raised to negative 1, or the inverse of the matrix in reduced form. Now all we needed to do is to multiply the matrix with its inverse and check if it results to an identity matrix. In the discussion, we will use intersection method to clearly show the operation. So for the first row of A and the first column of the inverse, we get A11 as 1 times 6/7 minus twice of negative 7156 plus 0 times 528 plus 2 times negative 67 over 56. Simplify the expression and get 1. Element A21 has 2 times 6/7 plus 3 times negative 71 over 56 plus 5 times 528 minus 1 times negative 67 over 56, which is simplified as 0. The third row, first column, will result to A31 as negative 3 times 6/7 plus 0 times negative 71 over 56 plus 1 times 528 minus 2 times negative 67 over 56, which is again simplified as 0. For the last row with column 1, we would have element A41, which is twice times 6/7 minus 2 times the negative of 71 over 56 plus 3 times 528 plus 4 times negative 67 over 56. Simplify the terms and get 0 again. Let's check the next column too, starting with the first row, giving 1 times 2/7 minus twice of negative 3 over 14 plus 0 times 1/7 plus 2 times negative 5/14, which is equal to 0. For the next row, we have twice of 2/7 plus 3 times negative 3 over 14 plus 5 times 1/7 minus 1 times negative 5 over 14, and this results to 1. Element A32 is solved next with negative 3 times 2/7 plus 0 times negative 3 over 14 plus 1 times 1/7 minus twice of negative 5 over 14, which is equal to 0. Then last is element A42 with 2 times 2/7 minus 2 times negative 3 out of 14 plus 3 times 1/7 plus 4 times negative 5 over 14, which again equals to 0. We are almost there, so continue with the third column, and from the first row, element A13 is then 1 times negative 1/7 minus twice of negative 15 over 56 plus 0 times 528 plus 2 times negative 11 all over 56, which results to 0. Element A23 has twice of negative 1/7 plus 3 times negative 15 over 56 plus 5 times 5/28 minus 1 of negative 11 over 56, and that is simplified as 0. For element A33, we have negative 3 times negative 1/7 plus 0 of negative 15 over 56 plus 1 times 5 over 28 minus 2 times negative 11 over 56. So it equals to 1. The last row with third column has twice of -1/7 minus twice of -15 over 56 plus thrice of 5 over 28 plus 4 times -11 over 56, which is again 0. The last column will complete the proof. So with the first row, we have element A 1, 2, with 1 times -3/7 minus twice of 25 over 56 plus 0 with 1 all over 28 plus 2 times 37 over 56, and it equals to 0. Element A24 has twice of -3/7 plus thrice of 25 over 56 plus 5 times 1 all over 28 minus 1 times 37 all over 56, and it gives 0. Element A34 has -3 times -3/7 plus 0 times 25 over 56 plus 1 times 1 out of 28 minus 2 times 37 all over 56, and this is equal to 0 again. The last element has twice of -3 over 7 minus twice of 25 over 56 plus 3 times 1 all over 28 plus 4 times 37 over 56. This is simplified as 1. So it is well proven that a matrix multiplied with its inverse ends up with an identity matrix of the same size.